Hello, this is my video about putting the randomness back into entropy. I'm Professor Ted Yu of Cal State University Long Beach, Chemical Engineering Department. Okay, so what is entropy? The general audience recognize entropy as a form of randomness. And this is something that we see in all types of pop culture. For example, I know the band Muse has an album called The Second Law, which talks about the randomness of the universe and its effect on society. So we know entropy as this force that takes something that's highly ordered, and when you increase entropy, it becomes more disordered. And this is used in basic science to explain things like why ice becomes water and all sorts of things. So this is something that in general we regard as a pretty cool phenomenon, that things in nature tends to become more disordered. So what do we learn more conceptually from high school? Well, we learn in high school that there's this energy called the Gibbs free energy, which describes a spontaneous process, and that anything that's less than zero is spontaneous. And there's two effects to it. One of them is enthalpy, which is related to heat, and the other one is entropy. And the delta S entropy increases if the disorder of the system gets larger. And similarly, if the order of the system gets larger, then the delta S decreases. So what we see here is that at high temperature, the positive change in entropy dominates the reaction, whereas at low temperature, the negative change of enthalpy dominates the reaction. So this whole concept of entropy as a randomness continues on in our high school chemistry classes. So what happens in college? Well, in college, this idea of thermodynamics is further expanded, and suddenly in physics and chemistry, we see the second law of thermodynamics. And this second law is basically described as the change in entropy equals the change of heat divided by temperature. Now, it's not until maybe a second or third course in statistical mechanics that we're introduced back to this entropy using the Boltzmann entropy formula, where entropy is defined as the Boltzmann constants times the microcanonical partition function. So what happens is that we have this concept of entropy as randomness, but then once we learn the second law, we see that, hey, why is this entropy related to heat? And it becomes a little bit confusing. And what we want to understand is why is entropy suddenly defined as a sort of inefficiency in the process and not entropy as randomness. So what is thermodynamics? So we're going to go back to the subject of this thermodynamics, the study of effects of work, heat, and energy on a system. Thermodynamics is only concerned with large-scale observations. So we learn about the zeroth law, which is thermodynamic equilibrium and temperature, as well as the first law, which is the relationship between work, heat, and energy. So all of this is very, at least from the zeroth law to the first law, is very conceptual. But then once we get to the second law of entropy, we have this relationship between heat and entropy. And that can be a little bit confusing, which I'll go over further on. And let me just go on to explain why this whole, the way that entropy is currently taught. So if we look at the thermodynamics history, okay, so we have all these famous scientists, Carnot up to Boltzmann, who derived all these equations for entropy. We see that all of the work was done prior to the Bohr atom model. So most of the principles were developed in the early 1800s without even a concept of what an atom was. So the outline for this concept of entropy that we're going to teach is that for the second law, we're going to start first with an atomic model and look at things microscopically. And then we're going to use this atomic model to describe how we derive a circular tetrale equation. And we're going to use this as the foundation for entropy. Now, this equation is typically taught in higher level classes, but it's very important to get a relationship between volume, quantum volume, and entropy. And the last thing we're going to do is we're going to instill intuition into every thermodynamic process by implementing a diagram that students can relate visually for several concepts, including entropy, temperature, and volume. So here's a brief demonstration of how that works and how we're going to be able to use a diagram to get concepts about how entropy, the particle, atom, and everything relates to each other. Okay, so let's go over how the second law of thermodynamics is defined conventionally. So the description from a typical textbook goes like, no apparatus can operate in such a way that its only effect is to convert heat absorbed by a system completely into work done by the system. It is impossible for a cyclic process to convert the heat absorbed by a system completely into work done by the system. And the second description is that no process is possible which consists solely in the transfer of heat from one temperature level to a higher one. So see how I highlighted the words no, impossible, no. So this is a very negative description of things. And what we want to do in this presentation is to describe things of more of what you can do and not a legalistic what you cannot do in thermodynamics. So instead of describing things from a mathematical point of view, we're going to start with the Boltzmann entropy formula. So what that it states is that entropy equals the Boltzmann's constants times the log of the microcanonical partition function. So here we see that the omega is described as the number of states and the number of particles. And what we can do here is that we see that, for example, for a system, and we're going to say a system of atoms, where there's 4 particles, and these 4 particles exist in 16 different states, we can define K as the number of particles, and we can define N as the number of states. But the question is, how do we define what is the possible number of states that these particles can occupy? So here we have how we're going to define a quantum volume from the Broglie wavelength. So what we're going to do is look at this particle which is described in our system, which is our atom, and we're going to find what the volume is. And this is something that's described in higher level physics class. And so the de Broglie wavelength is derived from the Planck's constant and the momentum. And the momentum is described from the kinetic energy of the particle, which is your atom. So from here we have a wavelength for the atom that's described by Planck's constant and the kinetic energy. Now in the non-relativistic case, the kinetic energy of the free particle equals to pi Boltzmann's constants times temperature. So we can substitute this in, and now we have the de Broglie wavelength as a function of constants, and the only variable is the temperature. So to cube the de Broglie wavelength, we have the quantum volume. So one of the takeaway message here is that the volume here is actually inversely proportional to the temperature. So using our binomial distribution, which we defined earlier, what we're trying to do is we're trying to figure out what is the large N, which is the number of states. So if we substitute the number of states as the total volume of the system divided by the quantum volume, this would describe how many states the atom can occupy. So if we substitute this here, we can use Stirling's approximation to take our quantity and simplify it so that we have a simpler quantification here. And then doing an assumption that the number of states that we have is much larger than the number of particles, we can come up with a simplification of the circular tetrale equation. So we're going to use this definition of entropy to describe all of our systems. So from the Sackur-Tetral equation, we could use it to describe the entropy of a monatomic gas, and we can develop shorter ways to solve this by making all the constants into one value. So what we can do is we could take out all the parts that are not dependent on volume temperature because they're all constants, and we can move it all out here, and we can call this a constant. And we can simplify this by calling the third part, which depends on only the number of particles and the mass, as phi. And using this definition, we have come to a definition of entropy that only depends on volume and temperature for a monatomic gas. So with this Sackur-Tetral's equation, we can use it to prove most of thermodynamics properties. So the first thing we can do is we could take the entropy and we can take a derivative with respect to volume. And when we do that, we get the quantity after substituting with the ideal gas law that ds over dv equals p over t. So if we manipulate this algebra, we get that at constant t, mass and number of particles, TdS equals pdv, or TdS equals dW. So what this means is that when we have a constant temperature, there's an exchange between this pdv term, which we know as work. And what is this exchange? This exchange, TdS, is what we define as heat. So from this, we can define that TdS equals the change in heat. So in a way, what we're doing here is reproving the second law of thermodynamics, that the change in heat equals temperature times the change in entropy. So now let's move on to understanding processes in thermodynamics more intuitively. So the key concept that we developed earlier was that the quantum volume is equal to all these constants times the temperature to the negative 3/2 power. So in a way, this is kind of like a non-intuitive result, because we think of volume, we think that, as the temperature increases, the volume should increase. So this is the first step for us to understand some of the effects of heat and how it changes a system. So if we look at a particle at low temperature, the red square represents the quantum volume, which is very large. And then if you have a middle temperature, the purple square represents a smaller quantum volume, because as the quantum volume decreases, the temperature increases. And then here we have a particle at high temperature. So moving on, we can see how the second law and Boltzmann's equation relate. Because if you look at these two equations, even after studying it in depth in a thermodynamics course, there's really hard to see how heat and entropy is related to this description of the Boltzmann's entropy formula, which is mostly about randomness. So we're going to describe simple processes with these entropy diagrams, which I described earlier. So just to reframe these diagrams, the inside boxes are the atoms, and the size of these atoms depend on the temperature. The outside box is the volume, and then we're going to see how omega changes at constant volume and temperature. Okay, so that's the microcanonical partition function that goes into the Boltzmann entropy formula. So in an isothermal expansion for a monatomic gas, we have du equals the heat capacity at constant volume times dt. So revisiting the first law, we know that du equals dq plus dt. So the change in internal energy is related to the change in work plus the change in heat. So at constant temperature, dt equals 0. So that means the change in internal energy is equals 0. So what we have, rearranging this equation, we have the change of heat equals the negative of the change in work, or PDV. So, so we know that if we put in heat in the system, as described in the second law, the entropy increases. But that's purely mathematical. What we want to do is see how, using these diagrams, if we undergo an isothermal expansion where the temperature is constant, you see that the size of these quantum volumes remain the same because the temperature is constant. But since the volume increases, the number of states increases because we have the same size particles, and now number of states goes from 9 to 16. So heat changes the volume without changing the temperature. So this explains how heat increases entropy when temperature is constant. So here we review the constant volume heating. So again, from the first law, the change in internal energy equals the change of heat plus the change in work. So if the volume is constant, there's no work. So at constant volume, we have that the heat is directly related to change in internal energy, which is related to change in temperature. Now that's all very much the same, but the new concept we have here is that this change in temperature actually results in a reduction in the quantum volume. So what we see here is that the volume is the same, but then if we add heat, the quantum volume actually decreases. And what this decrease in quantum volume does is that it increases the number of states from 9 to 16. And here we see a direct relationship between heat and entropy, in the sense that heat reduces the quantum volume by increasing the temperature. And this explains how heat increases entropy when volume is constant. So the last thing we're going to look at is what's called an isobaric expansion. And what that means is a constant pressure expansion. So using our ideal gas law, we see that we can rearrange it to this relation so that V over T equals constant, or this is called Charles' law. And as the volume increases, the temperature increases as well. So using our relation between temperature and quantum volume, we see that as the temperature increases, quantum volume decreases. So what we see here is that during an isobaric expansion, as the volume increases, the quantum volume decreases. And then as the vice versa. So the quantum volume is inversely proportional to volume in an isobar. So now we look at isoentropic expansion. So we know that the first law is, again, du equals dq plus dw, and that dq equals tds. So at constant entropy, dq equals 0. So what does that mean? That means that in order for this entropy to stay constant, we need this partition function to remain the same. So what that means is that the ratio of the quantum volume to the entire volume of the system has to stay constant. So what happens during an isoentropic expansion and contraction is that the volume increases proportionally to the volume change of the particle. That's to keep this volume over quantum volume relationship constant. So continuing on this concept of the isoentropic expansion, we know from our textbooks that the pressure and volume relationship in an isoentropic expansion is PV to the gamma power, where gamma is what's called a heat capacity ratio. So for a monatomic gas, the heat capacity ratio is 5/3. So what we can do is we can use our ideal gas law, and then we can plug in for our temperature. So for our temperature, we're going to use our definition of the quantum volume. So we get temperature equals to all these relationships, including the quantum volume, the Planck's constant, and Boltzmann's constant, and the mass of the atom. And from this definition of temperature, we plug it into our ideal gas law, and then we have a definition of pressure in terms of all these terms. Now, since we know that for isoentropic expansion, volume over quantum volume is constant, and also the number of moles is constant, we could replace V over quantum volume with C, a constant. Okay, so we replace it with C. Now, if we replace it with C and we move the volume over to the other side with pressure, what we see is that PV to the 5/3 power equals a constant. And in turn, we prove using our entropy diagrams that PV to the 5/3 is a constant for isoentropic expansion and contraction. And this will be used in the Carnot cycle, which we'll describe later. So for a Carnot engine, we can use these entropy diagrams to describe what's happening. So we have an isothermic expansion. As you can see, the quantum volume stays the same while the volume increases. And then we have isentropic expansion, where the ratio of the quantum volume and the overall volume stays constant. And then we have isothermal contraction, where the volume decreases, but the quantum volume stays the same. And then we have an isentropic contraction, where the ratio of the quantum volume to the overall volume stays constant. Okay, and one thing useful about this is that we could define this volume ratio that we've probably proved mathematically in our thermodynamics class, and we could see it from inspection that the ratio of VI1 and VF1 is equal to the ratio of VF2 and VI2. We can see this from pure inspection rather than going through a mathematical derivation. And similarly, we could do this for other types of cycles, such as the Stirling cycle, the Otto cycle, and the Diesel cycle. Here we describe the Otto cycle, which instead of isothermal expansion and contraction, we have isochoric cooling and heating. So, to conclude this lecture, let's see how we could use our thermodynamic diagrams to describe some of these negative descriptions of the second law. So in the second law, it says that it is impossible for a cyclic process to convert the heat absorbed by a system completely into work done by the system. So what I'm going to do here is present examples where cyclic work can only result in an increase in entropy. Okay, so if you look at an example where we expand gases in a piston, okay, and we're pushing it against an external pressure. In the first case, if we have an external pressure of 0, what we see is that since the external pressure is 0, the work is 0, and since the work is 0, the change in internal energy and change in temperature is 0. So pushing against 0 volume, the temperature stays the same. That means that the quantum volume stays the same. And as you can see clearly, as you push against an external pressure of 0, the entropy increases. So this expansion is what we call an expansion driven by entropy. Now similarly, if we do have an external pressure, what happens is that the system is doing work on the system, on the environment. So that means that PDV is greater than 0, and that means the change in work is less than 0. And then because we're in a constant in an environment where the change in heat equals 0, by the first law, we can relate the change in work with the change in internal energy, and that's less than 0. So the temperature decreases. So what we can do is that we see that as the temperature decreases, the quantum volume increases. So depending on the external pressure, the irreversibility of the work can be controlled, which leads to differences in the change of entropy. So this process is driven by energy. Now, if we take this process, okay, where we had irreversible expansion against an external pressure of 0, we see that you see here the temperature stays the same, but then if we push it back to the original volume, what happens is that the system has a pressure. So it's not going to be pushing against zero pressure. So what happens when you push against zero pressure is that the work is less than zero, is greater than zero, and that corresponds to an increase in internal energy and an increase in temperature. So if you go through this cycle, you see that this first step causes irreversibility in the system, because what happens when you push back is that the temperature of the system increases, and you can never go back to this original state. Once you have this increase in temperature and this increase in entropy, you can't go back here unless you take out heat or of the system. So this shows that when you have an adiabatic process where heat does not enter or leave the system, the entropy is always greater than zero. So let's look at the second description of the second law. So it says that no process is possible which consists solely in the transfer of heat from one temperature level to a higher one. Show how you can mix heat by increasing entropy, but not the opposite. So what we're going to describe here using our Sackur-Tetrel equation is, why is it that you could mix heat, but you can't really separate heat? Okay. So let's go to a simple idea. If we have two containers, and one is at 150 Kelvin, the other one's at 200 Kelvin, we know that the temperature will equilibrate to an intermediate temperature. The heat will mix, and they become an average temperature. But the question is, why do they mix? Okay, and the answer is entropy, but a lot of times the way that people explain it is not exactly correct. And let me just go over what people typically say when I pose this question. Okay, so the idea is that you have particles at 150 and you have particles at 200, and they're different particles. They want to mix together, and then they'll equilibrate to 175, which is the purple particle. Now, if you look at this from entropy point of view, sure, if you go from two different containers that are of different particles and you put them together, the entropy does increase. But overall, the internal energy stays the same, because the heat capacity times the temperature gives the same amount of internal energy. However, if you go back to this part, the last part, where these mixed particles become equilibrated at 175, again you have a zero change in internal energy, but the entropy actually decreases. So this last step will not happen. So that's why you can't really explain this concept of heat mixing by what you can say, this idea that it will just mix spontaneously because of this. So what we can do now is we're going to explain this using the Sackur-Tetrel equation. So if we look at the entropy of the system, we could just plug in all four of the systems with the Sackur-Tetrel equation. So that means the final state is the entropy of two boxes at 175, and initial state is the entropy of one box at 150 and one box at 200. So we plug it into the Sackur-Tetrel equation. All four volumes are the same. The only difference is the quantum volume, which is different for at 175, 150, and 200. So if we do some basic algebra, we could cancel out all the constants, and we have this number for the change in entropy. So we know that quantum volume equals all these constants times temperature. So all these constants cancel out. So our change in temperature, change in entropy, is now just related to the temperature of the final state at 175 with relation to the temperature of the initial states at 150 and 200. So is this delta S positive or negative? Well, that depends if the product of the final temperature is greater than the product of the initial temperature, 150 and 200. So what we can show by a simple mathematical proof about, kind of like the area of a square is always larger than the area of the rectangle when the perimeters are the same, is that delta S is always positive because TF is the average of TC and TH. So we define TF as TC plus TH divided by 2, and then the square of the average of two numbers is always larger than the product of 2. So what we can say here is that we define delta T as TH minus TF, and then from here we can define TC times TH equals TF minus delta T times TF plus delta T. And here we have TF squared minus delta T squared is your delta T. So in order to maximize this quantity, TF minus delta T squared, we see that it's maximized if delta T equals 0. So that means the final temperature is equal to example where delta T equals 0. So to summarize my talk, what we're trying to do here is to improve the teaching of a very important method, which is thermodynamics. And we want to put the concept of randomness back into entropy. And two things we're doing is we're using entropy diagrams, and also we're starting with the Sarkar-Tetrode equation. And I just want to thank some people. I want to thank California State University Long Beach and the Chem E 310 course, which has been kind of like my guinea pig for throwing out these concepts and teaching it in an undergraduate level. And I also want to thank Professor Brent Fultz of Caltech, who inspired me to come up with these concepts and try to come up with a relationship between the second law of thermodynamics and also Boltzmann's entropy formula.